Okay. Well, hello and welcome everyone to PyData Boston's June Meetup. For those of you who don't know, PyData is an educational program of a nonprofit organization called NumFOCUS. The global PyData network promotes discussion of best practices, new approaches, and emerging technologies for data management, processing, analytics, and visualization. We are a community of users and developers of open source data analysis tools, and this meetup is a forum for us to share ideas and learn from each other. We also approach data science using many languages, including, but not limited to, Python, Julia, and R. My name is Anita Yip, and I'm one of the co-organizers of PyData Boston. I'm excited to have Robert Ness with us here today to talk about causal modeling in machine learning. But before that, I want to touch on a few items. First, feel free to introduce yourself in the chat and in Slack. There's now an introductions channel in Slack. As we continue to hold virtual events, we want to continue building our community. Of course, if you have questions during the presentation, send them in the Q&A. At the end of the presentation, we can start having some real-time conversations and Q&As. So please turn off your microphone when you're not speaking at that time. Oops. Here we go. So you can find us here on social media. Feel free to tweet about today's talk using hashtag PyDataBoss. If you haven't joined our Slack community yet, please do so. This information is also on our Meetup page. As with all meetings, we want to reiterate that PyData is dedicated to providing a harassment-free event experience for everyone. Please behave professionally, as we do not tolerate harassment in any form. You can view the longer version of our code of conduct at this website. Feel free to reach out to any of the organizers if you have any concerns. So thank you for helping us to make this a welcoming, friendly community for all. Lastly, these meetings are only made possible with the help of volunteers. You can do anything from organizing an event by recruiting speakers or creating partnerships. We're back to meeting in person. You might also help secure venues and food. You can also volunteer to present and speak at one of our meetings. You don't have to have a full talk ready either, as the organizing team can help you through it. In fact, Robert filled out a Google form on our Meetup page saying that he was open to speaking. So I reached out and we made this happen. And with that, I'll turn it over to Robert to start presenting.
Great, can you hear me okay?
I can
Awesome.
hear you.
Well, hello everybody, thanks for joining. I'm just going to share my screen. Oh good, and I can see the chat. Oh, so when I have my, I'll ask you to kind of help me navigate a little bit. I'm going to use my keynote to present, and I won't be able to see you or anything happening in the chat. So I'm just gonna go, and then if you need me to stop, then stop me.
Sounds good.
Oh, says that you have disabled screen sharing.
Does that work?
Let's try now. Yep, alrighty. Okay, so I'm gonna try it this way. If I just select the keynote. Check. Can you see? Are you seeing like the presenter view or the regular the view for everybody? I can't tell. Is it looking okay? All right, awesome. All right. Okay, well, again, really happy to be here at PyData Boston. This is a 60-minute blitz on causal machine learning. It's based on the topics of a course, a workshop that I run on this topic at altdeep.ai. Enrollment for that workshop is open now if you're interested in enrolling. But it's really, I'm going to keep it really high level and kind of give you an impression of what causal modeling is, what its role is in machine learning, and how we program it using Python, and in particular a Python library that I'm quite fond of called Pyro. So first off, let me talk a little bit about who I am. I'm a machine learning research engineer. I focus on causal modeling and probabilistic programming. So I should also say I work a lot on natural language processing. Work mostly in Python. I write and teach at altdeep.ai. I did a PhD at Purdue in statistics. Focus there was on causal inference. I've published in places like NeurIPS. And I'm married to a really smart computer scientist. I'm fluent in Mandarin. I'm a published poet under a pseudonym that I'll never tell you. And I love functional programming in particular. That's if I could actually do that if there were more machine learning and data science languages that were more functional, I'd be a happier person. So to start, causality, causal inference, if you're coming from statistics or you're coming from, say, public health or epidemiology or economics, you might have seen some of this in your studies, in some of your training, but it's actually quite new to the machine learning community. But we've had a better articulation of the causal problems that we need to solve in recent years. So recently, Judea Pearl, who was a pioneer in generative modeling, probabilistic graphical models, as well as causal inference, he published a book, a popular science book. I really recommend it, called The Book of Why. And he talks mostly about the social science type of applications of causal inference. But then towards the end, he starts talking about artificial intelligence, and has this interesting story where he says, like, if a bot were vacuuming my house while I was asleep and I told it, you shouldn't have done that now, it's woken me up. I wanted to understand that it was the vacuuming that was at fault, but I don't want it to think that it should never vacuum again because that's going to make me unhappy. It should understand that it should have a causal model of the world. It should understand intent. It should understand enough causal abstraction to know that I'm upset now because you woke me up, not because you are vacuuming. Similarly, Gary Marcus, a renowned computational psychologist, came up with he has a book called Rebooting AI, wherein he quotes, we need to stop building systems that merely get better at detecting statistical patterns and data sets, often using an approach known as deep learning, and start building computer systems that from the moment of their assembly innately grasp three basic concepts: time, space, and causality. And the deep learning people are also realizing that this is a place that where we need to be solving problems, and that the problems are causal in nature. So this is Yoshua Bengio, who was one of the founders of modern deep learning. And this is him in a talk saying, once a machine can understand the causal structure of the world and produce plans to take advantage of the fact that they are not passive in the environment, but are active and can acquire knowledge, then we get to a better standard of application. So that means that they're understanding that, for example, doing something will lead to an effect. And so if the agent is active and can do that thing, then it can choose to do things that would give it more optimal outcomes. And so, but in order to make that kind of choice, it needs to understand or have some model of cause and effect. So now in most of the machine learning conferences, we see workshops, publications, and tutorials on causal modeling, causal inference. And we also are realizing that to talk effectively about the algorithmic bias and AI fairness issue, we need to have some causal abstractions that allow us to understand what's going on. So that image on the left there is taken from the ProPublica article that analyzed the Compass algorithm that predicted recidivism. Recidivism is is a phenomenon of describing whether or not somebody who is released from prison goes on to commit another crime. Somebody deployed an algorithm, and it was being used in a court system to predict, based on various features, whether or not an individual who was up for early release from prison would go on to commit another crime, and that was being used by judges to assess whether or not to grant that person release. And it turned out that based on this analysis, that if you found people that were alike in every aspect except for race, then, or every aspect that was under their control except for race, you would see higher predicted risk of committing another crime for Black people than white people. And in fact, there were some cases, such as these two individuals, where it was quite egregious, where the crime of this Black woman was a first offender, and it was a kind of a minor crime, while this man here was a repeat offender. You need a kind of causal semantics to make that kind of analysis repeatable and easy to use. So this directed graph here, it's a DAG, a directed acyclic graph, is a type of so we use this a lot as a way of encoding our causal assumptions about a system. This type of framework can be used to analyze whether or not an algorithm or whether or not a system is, for example, actively discriminating against a group of people, or maybe rather just reflecting lack of representation by that group of people in the pipeline that came into that system, in which case it would not be that system's fault. It wouldn't suggest that you need to change that system. It's a problem that came before the system happened. And so those are the types of, we need these types of abstractions to understand this debate. So I'm going to talk about what a causal model is and what exactly it can do that deep learning can't do. I'm using deep learning here, not because it's different from a causal model. We can build causal models with deep learning, but just because deep learning is what we consider to be the state of the art in machine learning. I'll talk about what the big tech companies are actually doing with causality. We assume that they're doing stuff with machine. We know they're doing stuff with machine learning, so we should be asking, all right, what are they doing with causal inference, and then maybe how does causality and machine learning tie together inside these organizations? Well, I'll answer the question of how you can learn how to get involved in causal modeling based on your existing Python-based skill set. Ideally, if you know a little bit of machine learning, that would help a lot. But I'll introduce to you some libraries to get started. And then I'll talk very briefly about the workshop and then open it up for questions. So what is a causal model, and what can it do that deep learning can't do? So to understand causal modeling, we need to understand the query. And by query, I mean, a query is something that we ask of a model. It could be just a prediction. It could be to infer that the value of some parameter, like in linear regression. But when we think about things in causal terms, we realize that there's different levels of query. So the basic level, which I call an association query, this is something that if you've done anything with machine learning or statistics, this is what you're used to. This is given some value of X, predict what Y is. All right, so given a feature, predict a label. Given some covariates or some predictors, predict the regressor or the outcome variable. All right, so in plain words, this would say something like, given someone on an exercise regime, what BMI are they likely to have? So if they go to, given somebody takes CrossFit or goes to Orange Theory, what is the probable range of BMIs that they're likely to have? Let's predict that, right? So deep learning is very powerful for this type of question, because if you give it enough data, no matter how many features you have in X, how multidimensional Y is, it can find some nonlinear high-dimensional association between X and Y. It can find some really high-dimensional squiggly line that's going to represent the curve on that XY relationship and fit that curve very well. Now, the next level is intervention. So intervention means you actually go and force a variable to take a certain value. And when you force something to take a certain value, it's no longer a random variable that's kind of moving in response to other random variables in the system. You've artificially broken that randomness and just fixed it as an external force on that system. And so here we're saying, like, let's suppose that we kidnap somebody and force them to exercise. How would that, what would the effect of that be on their BMI, right? This is exactly what we do in a clinical trial, for example, when we're testing whether or not a drug has an effect on a disease, or if we're running an A/B test where that randomization that we do in an A/B test is a type of intervention, and we're fixing the value instead of letting it be determined by nature. And so, but what this does is by artificially sticking your hand in there and fixing a variable, you're disrupting the data generating process, which means that you're disrupting the process that generated the training data, which means that if you just fit a model on the training data, unless it's a causal model, you're not, once you've done the intervention, you have now created data, you've created a situation that has deviated from the situation that you had during when the training data was collected. And so in order to make that work, in order to have prediction under intervention, we need an explicit modeling of cause and effect relationships. And finally, we have this idea of a counterfactual. So the query here is, given X, given a value for X, and given a value for Y, what would Y have been had X been different? So this is very much like an intervention. Another way of saying this is that we have an intervention where we force X to be we force X to have some value, predict Y, but that prediction is conditioned on some already observed value of X and Y that were different from what the intervention and what the intervention was. So so this is something that humans do a lot when they're reasoning. So if I say, given my current BMI, what would my BMI have been had I been forced to do that exercise regime, right? So it's now June. Had I signed up for the gym back in January, what would my weight be? When I make that kind of inference, that kind of prediction, I'm using information from what my weight is now. I'm comparing myself in this world to myself in a parallel universe. And this is very difficult for machine learning algorithms to do because they learn on data. They don't learn on could have been data. They learn on actual data. But we do this all the time as humans. We say, here's some outcome that I've experienced. I'm working at a company and I'm very happy. Had I chosen that other job offer, I would be less happy, or I would be more happy. And that's not based on actually having had that experience. Is based on a causal model in your head of how things would have unfolded had you taken that other opportunity. And so this requires not only an explicit modeling of cause and effect relationships, but a way to use the data that has observed to predict the data that could have been observed. So we often use the word twin worlds here. We have an observed world, we have a counterfactual world, and we need to make our inferences take into account evidence in the observed world and make inferences in the counterfactual world. So let's do some examples using, computer vision. So we're going to suppose that we have a generative model of computer vision, and it follows this kind of structure. And so at the basic level, we have pixels. This is the image that we see, and there are three causal factors here. So we've curated this data set so that there's images of people training, there's images of people bloodied, and there's images of people posing for, looking cool because they're boxing, right? Everything, I forgot to mention, everything here these are all boxers, right? And so we have boxers training, we have bloodied boxers, and we have posing boxers. We have two genders. well, at least in these images, we have two genders, male and female. And we have the handful of ethnicities in these images, in these examples, we have Black, white, and Asian, right? And that bidirectional, so those directed edges here, they imply causality. So that type causes what you see in the pixels, gender causes what you see in the pixels, etc. We also have, and that's bidirected edge there. I won't get into that, but it's something called, this type of graph with a bidirected edge is called an ancestral graph. But what it means is that there's some relationship, some unmodeled relationship between gender and ethnicity. So for example, that we might, that maybe some ethnic groups will have more representation from women than others. For example, there might be, you know, Muay Thai fighters might have more Asian women involved. So in this first case, an association, suppose that we randomly generate a bunch of pictures from this model. Because of just the way that the probability distributions work in real life, we're going to see that these samples will be kind of heavily skewed towards Black and white males, although we'll see a variety of types of images, so training, bloodied, and posing, right? Now, for the intervention, what we're going to do is go into our model and say, fix gender to female, and then generate again. And what would happen here is, in fixing gender to female, we might see some more variety in ethnicity. So that implies that ethnicity kind of flows causally from gender, or we might not. If we did not see variety there, we might conclude that the gender is determined, you know, that we have the gender makeup of boxers tends to come from a data generating process that has ethnicity as a higher cause there. But here again, so we're looking, we fixed gender, and we're seeing only female boxers, and but we see the same distribution of type, training, bloodied, and posing. Finally, we can look at the counterfactual example, which in this case, we've now generated an image, or we have an image, and say this image of this woman on the left. And now we ask ourselves, like, what would this, and her ethnicity is white. And so we say, what would happen if we were to refix her ethnicity to Asian? So this is, again, we're thinking about a parallel universe. We're kind of thinking about what would this person look like in some kind of bizarro universe where she's not white, but she's Asian. Now, you can get into how meaningful that is of an intervention. And that is a conversation we have in causal inference all the time. But what would happen here is that nothing else about the pixel should change. Like this, everything else that generated this initial image should be fixed, while only the elements, only the patterns in the pixels corresponding to ethnicity are permitted to change here. And so, so there in here you could, so if you refix it to Asian ethnicity and then sample, you get some variants here of the same woman, but with more Asian features. And so now we know that generative deep learning can do this. People do this with GANs, for example. And so what makes causal modeling different? In those GAN examples, I'm sorry, GAN means generative adversarial network, if you're not familiar. Those are these deep generative machine learning techniques that can generate hyper-realistic images. And so the interventions and counterfactuals in that setting, you can do that if you have specially curated data sets and special training procedures. And what you're doing there is effectively providing the ability to do interpolation between different sets of images. So this is essentially what deep fakes are doing. However, for that to work, you'd have to plan in advance what it is you want to do. You want to plan your use cases in advance and spend a great deal of effort training for all those, great deal of effort and data training for those specific use cases. A truly causal model can handle any causal query you throw at it, not just ones that you've kind of planned in advance. It should also take less data to train because there's more, that causal structure is built into the model. it should be less glitchy, and the component should be transferable across domains. And that turns out to be really important. In fact, if a causal relationship in nature is invariant, it doesn't matter, the relationship between altitude and temperature is the same as it is in the Himalayas as it is on the coastline. Because it's based on physics, right? So that type of invariance we expect to see when we're doing causal modeling, and that should help us with the transfer problem in machine learning. So talking a little bit more about interventions, let's understand why they're important and actually pretty ubiquitous in machine learning and probably the biggest use case for incorporating causal modeling in machine learning. When we deploy machine learning systems in production, the reason we do it is it's not just to have fun or to do cool models, or it's because we want to make decisions and decision making under uncertainty. And so when you make a decision, you're making an intervention, possibly in the process that generated the original data that generated the data that you are using to train your algorithm. And possibly not. So let's take an example. So here in this training block 1, what I'm doing is I'm collecting the readings of a barometer in the morning. So some kind of prediction or some kind of more weather readings. So humidity, just whatever I can say about the weather from sensors in the morning when I wake up. And then I record what the weather actually did that day a little bit later, right? And so what I want to do is be able to train a predictive model that says, like, all right, given these environmental readings that I take in the morning, predict whether or not it's going to be sunny today or it's going to rain today. Now, why do I want to make that prediction? Because I want to make a decision, and that decision is whether or not to take an umbrella with me when I go to work. Follow? Okay, so we collect some data, and so we run training on it, and then we deploy that application to production, and we start predicting some outcomes. So this first day, it told me don't take an umbrella, and I didn't take an umbrella, so that's what that check mark means, and I'm happy. The second day told me it was going to rain, and so I brought an umbrella, and it was right. The third day, it was wrong. Told me it rained, and it told me not to bring an umbrella, and so there was an error there, and so we have some errors. We have an error rate, etc. So the fourth day we're right. The fourth day we're wrong. Fourth day it's sunny and I brought an umbrella. Now I'll take that data and I'll feed it back into the training algorithm. So now I have block 1 and block 2 as my training data, and so I'm getting more data as I go, and hopefully the algorithm gets smarter and smarter. What's important about this is that the weather doesn't really care about whether or not I bring an umbrella. If I bring an umbrella, it doesn't affect the weather. But there are many cases where this type of predictive algorithm does lead to decisions that affect the data that's used to train that algorithm. An example, a very common example, would be in advertising. So in this case, I'm looking at a economic prediction, an outcome forecast, and I decide whether or not, based on that forecast, to increase or decrease my advertising spend. So I take that data and I feed it to the training algorithm, and then based on that first initial pass, I'm deciding whether or not to purchase an ad. So so in the first case, I don't purchase an ad, and revenue went up, so great. In the second case, sales went up. In the second case, sales was going down. It predicted that sales was going down, so I do purchase an ad, and that's the right choice. Third case, I predict the sales are going down. I don't purchase an ad. That's a wrong choice, etc. But what happens here is that every time when I run an ad or I don't run an ad, it affects the sales or the revenue that come in at the next time point, right? So I there's the choice. My algorithm is telling me to do things, either to purchase an ad or not purchase an ad, but that decision affects the data that I'm collecting in block 2 as I'm acting on the prediction. So data comes in, I get a prediction, I make a decision that affects the next data point that comes in. And so now the behavior of my algorithm is now feeding back into the data. I then retrain the data on this new block, on block 2, and I get this kind of feedback effect where I'm now the behavior of my algorithm is now part of the training of the process that generates the training data, and that is being used to retrain the algorithm, and then that repeats over and over again. We get like a negative feedback effect. This kind of thing happens in. So a great example of how this can be a problem is in credit card fraud detection. So if for example, you train an algorithm that can predict fraud, and then your algorithm starts blocking fraud, then the data that you collect is just the kinds of you get a whole bunch of cases of legitimate transactions and a few cases of fraud transactions, but these are a special kind of fraud that were smart enough to beat your algorithm. So now you're retraining the algorithm on those cases, and then you're going to start biasing your algorithm to more and more kind of outliers cases of fraud, and that can lead to problems. And then finally, we're using counterfactual modeling for making agents modeling agents that are making decisions under uncertainty. So this is bandits, this is Markov decision processes, this is reinforcement learning. What you see up here, if you're not familiar, is the Bellman equation, which is a key equation in reinforcement learning, and I rewrote it here to use a kind of causal modeling syntax, namely that do notation that you see in there. But the reason we want to do this is we want agents to reason like we do. We want our agents to reason counterfactually. So if, for example, we can look at, us as the modeler can look at some log data and say, all right, so based on these logs, had we given this agent a different policy of decision making, how much better would it have been had it done, on these instances that we've already recorded? That's a lot cheaper. Just asking that question and getting a good answer, it's a lot cheaper than actually running, say, an A/B test between two policies. Because if you're running the policy, then you're actually having to expend resources and time and perhaps profit by trying things out on actual users, as opposed to things that have already happened and you have a logged history of them happening. You can also do this in an online setting. You can have the agent kind of update its policy as it's making decisions and say, like, all right, looking back at its own history, you can say, all right, looking back at what I did, maybe 5 hands ago in this game of poker, I did what I made the decision that I thought was best at the time. And this is where I am now. This is the outcome that I'm seeing now. I think I would have gotten more reward, more utility, had I done a different action five hands ago. And so based on that conclusion, I'm going to update my policy so that when I hit similar circumstances, I'll make a better decision. So next question is, what are the big tech companies doing with causality? How does it tie into what they're doing with machine learning? So we expect Google and Facebook to be cutting edge of machine learning. Are they cutting edge of causal inference? The answer is yes, they are. But the strange thing is that within these teams at these companies, there's actually very little interaction between teams that are working on machine learning and teams that are working on causal inference. I personally think that's a problem, and I think it's an opportunity as well. So to understand exactly how this works, I need to explain a concept to you first. This idea called a causal reasoning engine. And once we know what that is, we can understand how it's actually deployed in industry. So we start with the causal model, and it has some causal assumptions. So this causes that causes this, and some parameters or weights, whatever you want to call them, that kind of quantify those relationships. Then once we have this model and we want to actually do some inferences, we have some observations, some evidence, some things that we've observed. We have a question that we want to ask, a query. First thing we need to do is check whether or not this question can be asked given this data. That's called an identifiability check. Turns out that in causal inference, a big question you have is like, I have this causal question. Can I even answer it given my data? And it's kind of if you're coming from a machine learning engineering background, that can sometimes be a hard thing to wrap your head around, is if you're used to being able to just kind of power through things with more data. And then we have an estiman, which is kind of like a recipe for calculating the answer to the query. And then we have the estimator, which is just statistics. Now that we know how to estimate the query, what's our estimation procedure going to be? So we have these causal assumptions. And the question now becomes, how do we represent them? A common way of doing that is with directed acyclic graphs, or DAGs. So they're a very nice, easy, straightforward way of representing your causal assumptions. So the nodes represent components or variables in a causal system, and the edge corresponds to a causal relationship. So here, this very canonical example you'll see if you look it up on Wikipedia, that the wetness of the grass is caused by both the sprinkler being on or off, or the rain, or whether or not it's raining. So let's pretend we're Netflix and ask ourselves some questions about our data. Netflix recently launched a show called Space Force, and it's a show that's produced by Netflix. Now, an association question, kind of bread and butter machine learning or bread and butter statistics. What is the probability someone who saw the trailer will go on to watch the show, right? So we can kind of just query the database, get some counts of people who, find people who watch the trailer, and then just count how many people actually went on to watch the show. Use that as like an estimate for the probability. That's kind of stats 101. Intervention question. What's the probability that somebody will watch the show if we show the trailer to them? So that's a little bit different from the first one. In the first case, we're actively choosing to show someone a trailer with the goal of making them watch it, as opposed to, say, for example, them stumbling upon the trailer, maybe by accident. Honestly, if they're in Netflix, there's, and the way Netflix works is that nothing happens in there randomly. There's everything's algorithmically driven. But you might have seen the trailer, for example, on YouTube, and then decided to go and see the show, or not see the show for that reason. But even in a case where Netflix is telling you, is doing, say, an A/B test, or is determining who to show the trailer to algorithmically, which is, so it's doing an intervention, there still might be some other issues, some things that happen in between watching the trailer and actually watching the show, right? And so, for example, so some kind of assignment mechanism has me watch the trailer, but then some things happen. I to make a decision about whether or not to read a review article. That decision is impacted by whether or not I saw advertisements for Space Force on Facebook or Twitter. Whether or not I saw advertisements for Space Force on Twitter or Facebook determines whether or not my friend recommends it, because these are social networks, right? So and then my friend's recommendation also impacts whether or not I go on to read that review article. So, and reading the review article and my friend's recommendations and whatever other exposure I saw in Twitter all goes on to impact whether or not I see the show, along with whether or not I saw the trailer. And so, but what you're really interested in this second type of question is that blue statistical association there, which is kind of muddled together with all that pink statistical association. So like the whole goal of causal inference here, which would be more specific, what we call this causal effect inference, is to kind of distill that blue from that pink. We want to know that direct relationship and isolate that from other confounding factors. Confounding is a term that we want to call these other factors here. And so And so causal inference in industry tends to be some experimentation and statistical techniques that make that blue statistical effect identifiable and in a way that minimizes bias and variance. And so these tend to be statisticians or people with, say, backgrounds in epidemiology or economics who have, where there's a whole kind of research methodology devoted to this question. We can also ask the counterfactual question. So this show was launched in May, and Robert, that's me, watched it. If they launched it in June, or if we watched it in June, or we as Netflix, would Robert still have watched it? So, the timing of launching these shows is very important at Netflix. So they want to know if I did watch it at some given point, can that tell them whether or not I still would have watched it at another time point? Or we might ask the question that Robert has watched the show. Would he have watched? What would he have watched otherwise? So if we did not recommend Space Force to him, what else? What would he have watched instead? Would he have watched other Netflix produced content? That's less ideal, right? Because then Space Force is merely cannibalizing off of other. It's cannibalizing its users off of other Netflix produced content. If it's taking me away from Netflix licensed content that's less profitable than Netflix, that's better, right? And if it's taking me away from a competitor like Amazon or Disney or HBO, that's best, right? So for now, we're going way beyond just like, all right, how many people watch this show to how many people have watched this show who would have otherwise watched something we don't want them to watch. So this is an example of a causal inference post to Facebook, probably a bit dated at this point, but so at Facebook and Twitter and many of these companies, it's often focused on marketing and advertising, asking, so for example, in marketing, there's a problem called attribution. That's fundamentally a causal inference problem. Also being used for features, like if I make this change to a feed, what will be the effect of the user's consumption of content on the site? And you need to kind of compare that to what the effect would have been otherwise if you had not introduced that feature, or to a baseline change, for example. Similarly, in this posting, we're looking for people who can do experiments on, or do causal reasoning on algorithms. So this is to say like, can we use kind of causal inference combined with statistical experimentation to understand sets of hyperparameters for an algorithm that would optimize its performance. So now I want to answer the question how you can learn causal modeling based on your existing machine learning or data science skill set. So I don't know if you can see me here. I have a bunch of textbooks here on causal inference. If you really wanted to kind of, the traditional way of learning causal inference is to, I don't know, grab a book like this or something like that and just kind of drill away at it, and it's like basically getting a master's degree in something that's unrelated to some of the stuff you've probably already been working on. So the real question is like, how can we get people to learn this stuff as a direct extension of their existing skill set? So to talk about that, I want to talk first a little bit more about these causal DAGs. Within the causal inference community, reliance on a DAG is a bit of a topic of debate. Everybody tends to agree that they're great for looking at, right? They're great for kind of saying like, I believe that this causes this and this causes that. They're great for visual representations of your assumptions that you can communicate to other people, that you can use to communicate with other people. Some people would like to use them directly in the causal reasoning engine, like we just did. So in other words, you're taking your causal assumptions and encoding them in a DAG, and then the algorithms that you use during inference are based on that DAG. Lots of people don't like that, particularly people from social science background, because the fundamental question is, what if your causal DAG is wrong? And that really matters in social science or public health because a wrong model leads to bad policy. But in machine learning, we love using wrong models. We do it all the time. We just will use a wrong model so long as it's useful, right? So this happens a lot in, say, latent variable models, or in other words, directed graphical models like mixture models, matrix factorization, hidden Markov models. These things have a directed acyclic graph representation, often in the form of plate models, so we can capture that multidimensionality. And they're implicitly causal, right? So like in this mixture model, we're saying that the data, there's observed xmn variable, the observed data comes from this switch, right? That's there's some kind of mechanism, this kind of switch variable z that determines which Gaussian mean or mixture distribution mean, that x comes from. So z is causing x in a certain way, while alpha, theta, and mu here are kind of weights for that causal relationship. And we usually don't treat this as a true causal model. My argument is that we could and we should. So I think there's a new opportunity for iterative model building. So the traditional way of model building in machine learning and data science is one that criticizes a model based on evidence. So this is the model build, sorry, the builds in, what does he call it? The build, compute, critique, repeat flowchart by David Bly, where you first build a model, or so this is where you put in all the structure and you kind of assume some kind of parametric form. You train it on data, and then you criticize the model. So criticizing here means I use goodness of fit, or I look at performance on some kind of prediction task, or I do posterior predictive check, or some kind of predictive check. I look at an information criterion, whatever it is. All of these things are just based on evidence, right? Like how well does my model explain the data that I'm seeing, right? And so that's it's kind of an evidence-based approach to building a model. We just iterated, trying to get models that are better and better fits for the evidence. I'm arguing if we take a causal modeling approach, it gives us an ability to criticize the model using falsifiability. So falsifiability is this idea from science, from Karl Popper here. So you can't prove a hypothesis, in other words, a model is true, or even have evidence that it is true by induction, but you can refute it if it is false. So to put it in common terms, that like if I observe some evidence and I come up with a model that explains it, I can't prove that model is true, but I can falsify that model. Because if, for example, if the assumptions of the model don't hold up against reality, then my model simply can't be true, and so I can falsify that model, and then maybe I could think about models that are harder to falsify. So causal models they are really easy to falsify. They have the set of assumptions that you build into a causal model are depending on the data you have, you can test those assumptions. And if there's a violation, if empirical evidence violates those assumptions, you have falsified your model. This is particularly true when it comes to interventions. If I predict that, increasing advertising will have a certain increase in sales, and then sales goes down, I falsified my model. And so we can do the intervention in reality. If I predicted advertising will increase sales, and then I do the advertisement and sales goes down, then I falsified my model. So if we do the intervention in reality and the outcome does not match the prediction, then the model is falsified. And we can, so if we can formalize our models as causal models, we can pick up that iterative model building approach, And what we do is, instead of trying to find models that fit the data really well, we try to eliminate models that are falsified by the data. And once we've eliminated all the things that we can falsify, then we kind of switch to an evidence-based iteration to try and optimize it. So this is a technique that made George Soros rich, in a sense. So George Soros is a billionaire trader, currency trader. He was Karl Popper's student, I think at London School of Economics, and he took Popper's theory of ideas about falsifiability and built it into his trading strategy, where basically you go on Bloomberg, you go on CNBC, and you see people telling you their models of how economics works and how finance works, and they stick by their models, and they're the ones who believe in this monetary theory, or they believe in that kind of thing. George Soros comes up with the model. He tries very hard to prove that model is wrong, and the second he sees evidence that it's wrong, he rejects it and updates it. So he said, "I'm only rich because I know when I'm wrong. I basically survive by recognizing my mistakes." When you have skin in a game like that, it tends to kind of favor this falsifiability-based approach. It's very easy in machine learning for us to move from generative models to causal generative models. It really just really requires us to take that structure of the model and use it as a way of encoding our causal assumptions about the system. So finally, I want to talk a little bit about the best libraries to get started. So in my course, I focus on two packages, one called BNLearn, which is in R, although there is a package called PGMPy in Python, which it has a completely different interface, but there's basically 90% overlap in the functionality. Well, that's not true. When it comes to evaluating causal assumptions, there's 90% overlap in the functionalities of these two packages. BNLearn is actually primarily concerned with learning structures from data in both causal but largely non-causal settings. So if you go to, I'll show you at the end of this, I'll show you some links inside of my GitHub repository where you can see some tutorials on this thing. The pros of this modeling approach is that it can handle interaction predictions, and you can do causal effect estimation. You can infer values of latent variables. Inference is relatively easy because you're working with a directed acyclic graph, and so you can rely on belief propagation and other probabilistic graphical model-based inference algorithms. And it's easy to reason on a directed acyclic graph. So again, both of these packages rely on directed acyclic graphs, and having the directed acyclic graph it comes in handy when you're trying to do inference algorithmically and when you're trying to reason on the system. Cannot handle counterfactuals, specifically the general kinds of twin world counterfactuals that I described earlier. They're not open world. An open world means that you have to specify in advance the number of variables in the system. The number of variables in the system can't be generated, say for example, through a control flow. So like if this variable is true, then there's 10 variables, but if there's 10 variables that have this outcome, but if that value is false, then there's one variable that has that outcome. You can having some control flow allows you to be a lot more flexible about the model in your modeling. Can't do that when you have a DAG. And these packages don't allow you to work with arrays or tensors, so you can't really take advantage of some of the advances in deep learning. We can go beyond the DAG with probabilistic programming. So I assume that the PyData group have seen some Python-based probabilistic programming languages before, like PyMC3 or Stan, for example. If you're familiar with Stan, is a standalone language, but it integrates in Python, and R. TensorFlow probability and Edward are other examples. In Julia, there's for Turing, Omega. Actually, the guy behind Omega, a guy named Zena, has a causal modeling version of it, which I think is really exciting, although it's still in a kind of research phase. Now, so the way to think about probabilistic programming here is that, it's a way of kind of making Turing complete causal models. So Bayesian networks are kind of generative models based on a DAG. Any causal Bayesian network you can represent in a probabilistic program. So the question becomes, now that we relax the assumption that you have to have a DAG, what advantage do you get from that added expressiveness? And so you can actually use the probabilistic programming to model very causal mechanism very richly, and then kind of analyze that when you're analyzing the control flow of a probabilistic programming. And you can also use recursion, for example, to have decision-making agents reason about themselves as part of a causal system, right? So instead of kind of thinking of, you have a standalone causal system and you have an agent that's reasoning about it, that agent can now become part of the system and make decisions within that system that take into account its own behavior. And so you can do that with kind of recursion, basically. And so one example of a kind of causal query you can answer here is counterfactual queries. Say, for example, there were 10 missiles fired and the radar detected all of them. But had there been more than 20 missiles, we would have missed at least one, right? So we have a kind of open-ended number of missiles, and we have an open number of, the number of missiles we might have missed, and we want to kind of put a probability on this statement that requires causal probabilistic programming. So in the repo, I got some, I used the Pyro package, and the Pyro package, it's a PyTorch-based probabilistic programming language. It's also there's also a NumPyro, which is based on NumPy. This is the only probabilistic programming language that I use that's open source. There's one that I use with the AI team I work with, but that's proprietary. That has explicit causal abstractions built into the programming language, namely a do operator, if you know what that is. And so it's if you go, so you can handle counterfactuals, and then you can do the other things that you can do with the Bayes net. And then of course it's based on PyTorch, so that's multi-dimensionality, working with tensors and using that you can do with deep learning and working with inference frameworks such as stochastic variational inference. That it allows you to do all of that to answer causal queries, which makes it very powerful. It can also handle these open world settings like I just described. But they're hard, the second you get rid of a DAG, things become a lot harder to reason about, and harder to do inference. So one of the challenges of probabilistic programming, I'm hoping we'll probably get better at this in the future, but you'd like to be able to kind of specify a model of arbitrary complexity and then just have inference work in real life. You have to kind of write your own inference algorithm. It can be pretty tough, especially if you're trying to reason counterfactually. So talk a little bit about the workshop that I teach. It covers all these topics. Enrollment's open now if you're interested. It ends in 4 days. But we touched on generative modeling, causal inference, causal agent modeling, kind of graphical modeling theory. Basically everything you need to know to wed these two universes together, this causal inference universe and this generative machine learning universe. And you get to communicate with, you get access to me and the other instructors. So when you have questions and you need help with the homeworks, you'll learn how these causal inference algorithms are applied in top tier technology organizations. If you've worked in causal inference, if you try to learn causal inference, you see all the examples are usually about drugs and healthcare and stuff like that, which are of course very important applications, but a lot of the people in my audience are much more interested in saying, doing the kind of things that we saw in those job descriptions for Netflix and Facebook. And of course, we're using those probabilistic programming languages, those Python libraries, as opposed to using kind of black box packages for causal inference. So we're building the models ourselves. I have a PyData 10% off course code if you're interested. There's two pricing plans, one for the full price and one for monthly payment. So those are the coupon codes. Because this is recorded and it'll go out, and I'll put a 24-hour limit on this. Cool. Are there any questions? I guess I'll stop sharing. Actually, let me show you. I think, can you still see my screen? No, I'm going to show you the repo. So the course, you got to pay for it, but the, where is Zoom? When you have multiple screens and then you're trying to use Zoom and you got to look everywhere for this bit or that. Am I still sharing? Can you see my screen? Nita, can you nod your head if you can see my screen?
Yeah, I can see your screen with the thank you.
Okay, that's wrong then. Let me say, all right, stop sharing. Share, desktop 2, share. Okay. So this is the repo. Of course, you got to pay for it, but everything in the repo, you can just, it's open there on GitHub under an MIT license. So namely, we have some tutorials here that you can run through. So this is an reinforcement learning example, one with a variational autoencoder. I actually have there's a PR that I'm about to push through that'll have a whole bunch of updates here where you actually can see some of past student project work. And so you can see some of the analyses that other people have done here. So this is an analysis where people have tried to come up with a causal model for predicting what kinds of what kind of house you should buy in order to optimize return on Airbnb rentals. Another one where some students were coming up with a object-oriented programming approach to causal modeling and a ORM mapping to a database so that you can have kind of a knowledge base of causal relationships and then kind of instantiate those into models and be able to do interesting things. This is done by, this Moneyball here was done by some students who were interested in soccer and wanted to predict, find causal effects on, find the causal relationship between certain factors and the transfer price of ball players. This is using a latent variable model called a deconfounder model to try to predict the box office output of the box office revenue of a movie based on deciding whether or not to cast an actor. So the problem here is to say, we could see a correlation between actors and the revenue for movies, but some movies have actors and actresses in them where we wouldn't expect them to actually have a causal relationship with the box office revenue. So one example might be the actress who plays Mrs. Moneypenny in James Bond movies. Bond movies tend to gross really high. She tends to only be in those movies, so she's very correlated with high grossing movies, but we know that there's some confounding there. There's the James Bondness of the movie is really why that movie is making that much money and why that movie has her cast for it. Similarly, there's that woman, her name escapes my mind, who plays Robin in How I Met Your Mother. She's in all of those Avengers movies, but we can, so we might say like, wow, whatever movie she's in tends to like break box office records. But that's what machine learning would tell us, but that would be what causal inference which should tell us otherwise. And so we want to be able to train models that can make that kind of understanding. Here's some recent work on modeling the effect of interventions, namely stay-at-home policies in an epidemic, using compartmental models for epidemiology. And then we have some reinforcement learning examples as well. Any questions?
Thanks so much for your presentation. During, while you were talking, there are people who asked some questions already in the Q&A. So we'll just go through those and then we'll have a back and forth talk with our attendees here. So Michael asked, would you recommend using causal modeling if you only have observational data?
Yes. And so it depends, of course, on the objective. But I personally prefer using causal modeling for any modeling problem. What that means is, so put it like this. So if you've read a book on, say, generative machine learning. So Riley recently has a book on generative deep learning, or generative deep learning. And the whole first chapter is talking about thinking about the data generating process and its relationship to the underlying joint probability distribution of everything that's inside your data. And this is kind of the philosophy of probabilistic programming as well. You want to be thinking about the process that generates the data. And the fact is, just because of the way the human brain works, you really can't think of a data generating process without applying some kind of causal theory to it, right? Like, for example, a topic model. The topics cause the appearance of words in the document. And so you should, so if you have just observational data, I would suggest, write out a DAG that kind of represents that the relationships between those variables and any latent variables that are not captured by that by your data set that you believe are nonetheless part of the data generating process and need to be modeled explicitly. Now, once you have that DAG, you can ask the question of whether or not if you want to ask something causally of your data, like, for example, does this variable cause that variable? You can ask, causal inference will tell you, given this DAG, can I even answer that question given the data that I have? And then if I can, it'll tell you some formulas for calculating that causal effect. For example, the adjustment formula.
Thank you. Next question is, can you recommend some resources or case studies to read more about causal inference, attenuating data feedback effect, and maybe the relationship of that with concept drift, if any? So for example, when you detect concept drift, you have to retrain and update your model, but it might affect your model in the way that you described with the fraud model.
Right. So I don't know of any, there's very little literature out there for fusing causal inference style reasoning into concrete machine learning problems. Most people in the machine learning community right now are thinking about either two things. One is like, there's a relationship between two variables and I want to just figure out which way causality goes. Number two is in latent variable models, like say, variational autoencoders are often interested in disentangling factors inside the latent variable, which was implicitly a causal question, like they want to figure out what are the causes and can we separate them out. Now, but kind of capturing things like concept drift, I think the I think the best place to go would be, aside from my stuff, this book doesn't talk, this is Peter Jansing and Shokoff's book. They don't talk about this issue directly, but it's the best book that I've seen, the best published book that I've seen in terms of connecting causal modeling, causal inference to bread and butter problems in machine learning. I think that'd be a good place to start. To get, if the credit fraud problem is kind of close to the problem that you're working on, most people in industry who attack that kind of problem use something called propensity score matching. So if you start Googling around propensity score matching, that might come up with some techniques that could solve your problem if the two problems are related.
Great. So the next question is, which companies are working on the causal inference and learning that DAG?
So learning the DAG. So there is a problem in causal inference called causal discovery where you're trying to learn the DAG structure from data. And so I've written some papers on this, and causal discovery is a popular method in systems biology, computational biology. So any kind of computational biology company that is interested in understanding the structure of regulatory pathways in molecular biology. So this could be synthetic biology companies like Ginkgo Bioworks. This could be Daphne Kohler, who wrote a whole book on probabilistic graphical models, and she's now CEO of a machine learning / biology company. I think it's called In Citro or In Citro or something. I forget. There's also one in Boston called GNS Healthcare. They also do some DAG discovery. I've talked to some people at Quantum Black, which is the data science arm of McKinsey. And turns out that they were interested in doing causal discovery, learning DAGs from data. And so that would obviously be in business applications. That surprised me when I discovered that. I didn't know people were actually using these techniques in that domain. But other than that, I think in most practical problems, almost a better way to go, is to actually, rather than try to, learn DAGs from data, which tends to be really hard when there's missing variables, which is almost always. I think it's good to try to come up with your own, do some experimental data analysis and understand the structure of the data, and then combine that with your own domain knowledge to come up with candidate DAGs, and then try to falsify those DAGs based on your data. I think you can combine that with those discovery techniques, but in my experience, particularly in kind of machine learning examples, it's better to try to use your own kind of human, wetware to come up with DAGs as opposed to rely on algorithms. But you can use algorithms as a support.
Thank you. Ronald asked, is it possible to learn causal relationships that we can't explicitly define yet? I do know that we can learn DAG structures that fit training data, but I was just curious if there are any other methods that might work better.
So there's a difference between mechanism and causal relationship. So every causal relationship has an underlying mechanism, but it might not be necessary for us to learn that mechanism. And oftentimes we can't learn the mechanism without, scientific experimentation. But we can find and operate on just the knowledge of the causal relationship itself, and that might be enough. Example, this happens a lot in biology, right? So there are many drugs that have been around for a long time where people don't particularly understand the mechanism of action, right? I think aspirin is one of those examples, and there are several others, but this is something that we've been taking. People take this, and it's well understood, and there's lots of studies on it. And yet, if you try and go in there and figure out exactly causally how the aspirin is relieving the headache, there's actually not that much knowledge about what that mechanism looks like. But that's enough for us to know that we still know that taking an aspirin will cure a headache. And so there's probably, depending on your application, it's the reason when you really need, counterfactual reasoning often requires some specification of mechanism. But really, if you're just trying to understand, say, the causal effect of this thing on that thing, especially in applications like in advertising and A/B testing and sequential decision making, simply kind of knowing that there's a relationship between two things is often enough. I think if that doesn't answer the question, let me know.
And the last question is Giuseppe likes books and paper and is wondering if you can suggest some good books or influential papers.
Sorry, Giuseppe likes books and paper. Oh, okay. Oh, Giuseppe likes books and paper. I see. Yeah. So. So paper is like not going to unearth my big mountain of unread papers. It's just going to make me feel bad. But I will tell you. I'll show you. These authors that I'm about to show you will have good books. So Judea Pearl, obviously is a very important person in both generative machine learning and in causal inference. This is his textbook on the subject. This reads like an encyclopedia. It's the kind of thing that you buy and then kind of consult. It's not, it's hard to read cover to cover. For that, you can read his popular science book, as I mentioned, called The Book of Why. But as I mentioned, Peter Jansing and Shokov's book, Elements of Causal Inference, is probably my favorite textbook. There's O'Reilly has a book. It's probably dated at this point. This is written by Samantha Kleinberg, so this would be more towards the economics and statistics kind of approach to causal inference, less the generative modeling approach that I've described here, but also a good read. Also, for a more technical introduction by Pearl, this primer by Pearl, Glamour, and Jewell, Causal Inference in Statistics, very thin. This is, reading the Book of Why and then reading this and then kind of having causality there when you want to kind of go into the proofs and stuff like that. That's a great way to go, I think.
Someone snuck in one last question. Could you discuss what the ideal prerequisites would be for this course and how to apply the discount for the course?
So I could put those coupon codes, or maybe I'll just, yeah, so those coupon codes I gave out, sorry, let me talk about prerequisites first. So you should know what joint probability is and conditional probability is, what expectation is, expected value, and variance. So really just kind of those basic elements of, I guess you would call that probability theory. So like, random variables, joint probability, conditional probability, Bayes rule, expectation variance, and not so much all the properties and mathematical relationships between those things. You just got to know what they are, and aside from that, and then if you're comfortable with Python, which I assume you are if you're on this call, that would make things a lot easier if you're working on the homeworks and the capstone project. But yeah, and that's about it. Everything that we do kind of we'll build on is basically core concepts of joint and conditional probability distributions. As for the coupon codes, when you go to the checkout page, there should be a place to apply the coupon codes. Reach out to me on robert@altsdeep.ai. If there's an issue and you can't get it to work, I can paste those codes again in the chat if you missed them.
Yeah. With that, I'm going to unmute participants in case there are other questions that have come up that people just want to ask real time. So hopefully at this point, people should see that they have the ability to chat. Robert did put his coupon codes for his course on the chat as well. Anyone else have questions? Going once.
There's a new message. Will a recording of the session be available?
So we will make the recording available at some point. We have to figure out how to get that to everyone though. So, but we will have your slides to send out fairly soon, right?
Yeah.
Okay. So we do have plans to make that available to everyone, both the slides and the recording. Great. Sounds like there are no other questions.
This is the part where we usually like have banter and then like eat pizza and stuff like that, and now I don't get to do that because of COVID. So I wish there were a Zoom equivalent to that.
Yeah. Well, thank you everyone for joining. Thank you, Robert, for presenting, and we hope to see you at our next PyData Boston event. Take care.
Thank you.